In this video, we're going to talk more about what a derivative is, and this will be the basis for everything we do for the first half of the year. So we've already talked about everything at the top. We should know, hopefully by now, that average rate of change means the slope of the secant line. And as a reminder, the formula to find the slope is y2 minus y1 over x2 minus x1. So if we look down here to a more general example, we use a lot of variables and function notation. So if we choose x to be our first x value, when we plug it into our function, our y value then is called f of x. So that would be the coordinates for that point there. So x, f of x. If we were then to choose another x value that is somewhere past our first, we don't know how far, it should be hopefully some small change. We may call that delta x, is the space between. Again, that just means a small change. Then our new x value would be called x plus delta x, because we've gone that far plus whatever delta x is. So if we plug that into our function, then our y value for this ordered pair would be called f of x plus delta x, so that we then have a second ordered pair. And so these are two ordered pairs that are both on the function. They're also on the blue line that's called a secant line. If I were to then find the slope of the secant line, I would use this formula. So my formula says I'm going to take my y values and subtract the two. So I'll have f of x plus delta x minus f of x. And then in the denominator, I'm going to take my two x values and subtract them. So I will have x plus delta x minus x. If I simplify these just a bit, I do see that my final slope formula is this big ugly guy here. So please don't let that confuse you. This is literally just a very fancy way of saying the slope formula. In the numerator, we have our change in y. So you can see that's like my y2 minus y1. In the denominator, the very definition of delta x means the change in x. And the way we find change between two numbers is we subtract them. So this is just another way to find the slope formula. Okay, so when we talk about a derivative, we have this really big, ugly formula. And what the derivative is the slope of now a tangent line. So in the past, we've always dealt with secants. A secant line is going to cross in 2 points. A tangent line would cross at 1 point. And so let's look to see how, where this formula comes from. So if we look here, I have h, which I'm using here to represent delta x. That's how far apart the purple dot is from the green. M is going to be the slope of the green. So I'll actually put that in green here. This is the slope of the green line. My function is f of x. And then the derivative is going to be the slope of the tangent line. So what we're going to be doing in calculus is, we have a slope formula for the green line. If we can take this green point and move it so that it's very, very close to the purple, we've now created a tangent line, and we need to find the slope of that. However, if the green is on top of the red, that creates a problem, because the way we calculate the slope of the green line is to take the change in y with the change in x. Well, if I move the green on top of the purple, there's no change. You can see now my slope is undefined. Okay, in the green circle there, it's undefined, it does not exist. So what we have to do is we have to use limits. And what we're going to do is we're going to say, what happens when the distance here between the purple and the green approaches 0? What happens if I move this, and you can see it there, my delta x is approaching 0, and you can see my slope actually gets closer and closer to the derivative, which is the slope of the tangent line. So as I get really, 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 really close to the purple, that slope is getting closer and closer and closer to the actual derivative. And you can see until it actually hits a point where it can't move any further. So that's really what we're doing. So if we go back here to our definition, we're going to say what happens as that distance between my points approaches 0. So notations, these guys are really common. These two are the most common. This one's probably the most useful. This is read as the derivative of y with respect to x. And the other ones are just other things you may see. They don't mean anything different. So we're going to do one example. We're going to find the equation of the tangent line. So a tangent line is straight. So we need an equation of a straight line. And we know the slope of this line is going to be the derivative. So first we need to find the derivative. And to find the derivative, we use the definition of the derivative. So first, we need to find f of x plus delta x. And all that means is we're going to take this and plug it in any place we see a variable in the function. So we're going to have, instead of x squared plus 1, we're going to have x plus delta x squared plus 1. Then we're going to subtract the original function. And the original function is this entire thing. In the denominator, we have delta x. So remember, this is going to find the slope of the secant line. In order to turn that into a tangent, we're going to take one point and we're going to make it really close to the other. So if we tried to find the limit, we always try direct substitution. We're going to end up getting that 0 in the denominator. So we need to do some simplifying. So we can FOIL. So if we use the square of a binomial pattern, we can take a little shortcut. And that's just a pattern. If you FOIL, you'll get the same thing. So I carried down my plus 1, and now I'm going to distribute this guy. Okay, and I'm just going to keep working in the numerator here. So I have x squared minus x squared cancels. 1 minus 1 cancels. And I'm left with these guys. And remember, I'm still trying to find the limit as delta x approaches 0. And I still have a 0 in the denominator when I try direct substitution. So what we can do is we can actually factor a delta x out of the numerator. So that I get delta x times 2x plus delta x. And now that I've done that, I can cancel. And then to evaluate this limit, all I have to do is direct substitution with this problem here. So I'm going to plug in 0 for delta x, and I'm left with 2x. So this is the derivative of f. And remember, that's at any given point. So now they wanted me to write the equation. So I can use this to find the slope of the tangent line. My ordered pair is 1, 2. So in order to find the slope at that point, I have to plug in this x value here. So the derivative, which is the slope of the tangent line at 1, is going to be 2 times 1, or 2. So this is the slope of this line, and this is a point. So the most logical form would be to put this in point slope form. So I'm going to say y minus my y value equals the slope, x minus the x value. And this will give me the equation of the tangent line. So just to show you real quick, differentiability, if it's differentiable, it has to be continuous. So here's some examples of things that are not differentiable. This guy is not differentiable at every point because there are lots of places here where it's not continuous. So this guy is not differentiable. If we have something that comes to a sharp point, it's not differentiable. And the reason is because the derivative coming in on this side is negative, and the derivative coming on this side is positive. So the derivative does not exist. What that creates is this any type of a sharp point. And then also if we have a vertical tangent line, again, remember the derivative is the slope of this tangent line, and vertical lines have a slope that's undefined.